On December 24, 2024, a spacecraft the size of a small car became the fastest object human hands have ever built. NASA's Parker Solar Probe, diving past the Sun at a distance of about 6.1 million kilometers from its surface, reached a top speed of roughly 692,000 kilometers per hour, 430,000 miles per hour. That is fast enough to fly from New York to Tokyo in under a minute. It is faster than any rocket, any jet, any bullet ever fired, and it only reached that speed because the Sun's own gravity did most of the work, whipping the probe around on a series of close solar passes after a boost from repeated flybys of Venus. And if you pointed that same spacecraft, at that same speed, toward the nearest star beyond our own Sun, Proxima Centauri, 4.24 light-years away, it would still take roughly 6,600 years to arrive. That's the paradox at the center of everything that follows. Our fastest machines are incomprehensibly fast by any human measure, and still immeasurably slow by the measure of the universe. The usual story about interstellar travel is a story about speed. Build a faster engine, and the years fall away. But there's a second problem hiding underneath the first one, and it may be the more serious of the two. Space gets more dangerous, not less, the farther into it you go, and the very physics that could shrink a multi-thousand-year trip into a human lifetime is the same physics that turns ordinary hydrogen into a lethal weapon. That trade-off, speed against survival, is the real subject of what follows. Subscribe if you want more of this, and let's begin. To understand why distance itself becomes a hazard, start with how far we've actually managed to get. In 1903, the Russian schoolteacher and self-taught engineer Konstantin Tsiolkovsky published what's now called the rocket equation, the relationship between a rocket's change in velocity, the speed of its exhaust, and the fraction of its total mass that has to be fuel. It is still the equation every real spacecraft is designed against, and it is unforgiving. Chemical rockets, the only kind that has ever carried a human being off the Earth, top out at exhaust velocities of around 4.5 kilometers per second. To reach any meaningful fraction of light speed on that kind of engine, a ship would need to be almost entirely propellant, with a payload measured in single-digit percentages of its launch mass. The Saturn V, still the most powerful rocket ever successfully flown to carry humans, lifted off at a mass of nearly 3,000 metric tons and delivered only about 43 metric tons toward the Moon, a payload fraction of roughly 1.5%, and that was only for a 3-day trip across a few 100,000 kilometers. For any realistic interstellar mission, that math simply doesn't close. Modern electric and ion propulsion systems improve on that picture, but only modestly. They trade thrust for efficiency, producing gentle, sustained acceleration over months or years, rather than the raw exhaust velocity that would actually matter for an interstellar crossing. And they're already the technology behind real missions flying today. None of it changes the order of magnitude. What we've actually achieved, across nearly 70 years of spaceflight, is Voyager 1. Launched in 1977, it used a sequence of real gravitational slingshots, close flybys of Jupiter and Saturn that stole a sliver of each planet's own orbital momentum to reach a cruising speed of about 17 kilometers per second relative to the Sun, roughly 61,200 kilometers per hour. It is, at this moment, the most distant human-made object in existence. As of 2026, it sits around 170 astronomical units from Earth, about 25.4 billion kilometers away, far enough that a radio signal now takes more than 23 hours to reach it, and by November of 2026, Voyager 1 will cross a real milestone, becoming the first human-made object to sit a full light day from home. At Voyager's actual speed, the trip to Proxima Centauri would take on the order of 75,000 years, roughly 3,000 human generations, each one living and dying without ever seeing the destination arrive, a span longer than the entire history of agriculture, writing, and every civilization that has ever existed, several times over. That is the honest baseline everything else is measured against, and every attempt to beat that number runs straight into the same wall. The farther you go, the worse space gets. Imagine, for a moment, that every one of those propulsion problems has already been solved. Infinite fuel, a perfect engine, whatever cruising speed you want. It wouldn't matter. The universe has a second, entirely independent gate, and it has nothing to do with how the ship gets moving. Start with radiation, because it doesn't wait for relativistic speed to become a problem. It's already serious on a completely ordinary, slow, chemical rocket trip to Mars. NASA's Curiosity rover carried an instrument called RAD, the Radiation Assessment Detector, through its 253-day cruise to Mars in 2011 and 2012, and it measured a steady background dose of galactic cosmic rays, high-energy particles, mostly protons, flung across the galaxy by exploding stars and other violent events, averaging about 1.8 millisieverts per day. Carried across a full round-trip Mars mission, that works out to roughly 0.66 sieverts of accumulated radiation from transit alone, before a single day is spent on the Martian surface. A sievert is simply the unit that measures biological radiation damage, scaled for how harmful a given type of particle is to living tissue. And a whole body dose of 1 sievert is associated with about a 5% increase in lifetime fatal cancer risk, with acute doses well above that threshold capable of causing radiation sickness outright. Spaceflight agencies keep astronaut career exposure limits well under the 1 sievert mark. For a sense of scale, a person standing on Earth absorbs an average of roughly 3 millisieverts a year from natural background radiation combined, meaning the 1.8 millisievert daily dose Curiosity, measured in transit, is on the order of 200 times what an ordinary day on Earth's surface delivers. And that number doesn't even include solar particle events, the sudden, unpredictable bursts of high-energy protons a major solar flare can throw off, capable of spiking the dose rate far higher for hours at a time, with no reliable way to predict exactly when the next one will hit or how severe it will be. A round trip to Mars, under calm conditions, already consumes a substantial share of a human being's entire allowable lifetime radiation budget. And Mars, on the scale of this conversation, is next door. It gets worse once you leave the sun's shelter behind entirely. On August 25, 2012, at a distance of 121.7 astronomical units from the sun, Voyager 1's cosmic ray subsystem recorded something researchers had never measured before. The flow of low-energy particles native to our own solar system dropped to essentially zero, while the population of high-energy galactic cosmic rays, particles born outside the solar system altogether, jumped to occupy nearly the entire local particle environment. Follow-up plasma measurements confirmed the same transition from a different angle. The density of ionized particles around Voyager 1 turned out to be roughly 80 times higher than typical densities inside the heliosphere, the magnetic bubble the sun inflates around the solar system that deflects a meaningful share of incoming galactic radiation. A separate instrument, Voyager 1's plasma wave subsystem, added a third confirmation between 2013 and 2015. As the spacecraft pushed deeper into interstellar space, the local electron density it measured rose roughly 40-fold. 3 independent instruments, 3 independent measurement techniques, all telling the same story from different angles. Inside the heliosphere's bubble, we are partially shielded. Outside it, we are not. And the ceiling here is a hard one. There is no material shield, however thick, that fully stops galactic cosmic rays without adding so much mass that it defeats whatever is supposed to propel it. Every additional stretch of distance from the sun is, quite literally, a stretch with less protection, and Voyager 1's own instruments were the ones that first put a number on exactly how much. So what happens if a mission actually tries to go fast? Genuinely, relativistically fast, the kind of speed serious interstellar concepts are built around. Consider Breakthrough Starshot, the real, ongoing research initiative, first proposed publicly in 2016, aiming to push gram-scale probes, accelerated by ground-based lasers, to roughly 20% of the speed of light, for a flyby of the Alpha Centauri system. The concept calls for a ground-based laser array delivering more than a gigawatt of combined power, focused for about 10 minutes on a sail roughly 4 meters across and only a few hundred atoms thick, carrying a probe weighing around 10 grams, light enough that a fleet of 1,000 of them could, in principle, ride out from a single mothership. 20% of light speed isn't an arbitrary number. It's roughly the point where a real human research career could plausibly span both the launch and the arrival of data, since even a successful flyby would still need over 4 years just for its own signal to return across 4.24 light-years, on top of the outbound crossing itself. Done successfully, it would cut the trip to Alpha Centauri from roughly 100,000 years at conventional rocket speeds down to about 22 years. But at that speed, the spacecraft itself becomes the hazard. A 2016 physics analysis of relativistic spacecraft moving through the interstellar medium modeled exactly what happens when a probe traveling at 0.2 C plows through the thin scatter of gas and dust that fills the space between stars. Ordinary interstellar hydrogen and other atoms struck at that velocity deposit enough energy to gouge microscopic craters and tracks into a solid surface. The analysis found that a quartz surface, after sweeping through a gas column of roughly 2 quintillion particles per square centimeter, a thickness of interstellar space a fast probe would cross within a handful of years, would be etched about 1/10 of a millimeter deep. Dust grains, far rarer but far more energetic per impact, could erode a similar surface layer 0.5 millimeter thick. For a sail only a few hundred atoms thick to begin with, either number is not a cosmetic scratch. It's a meaningful fraction of the entire structure. Graphite held up considerably better than quartz under the same bombardment, which is why serious probe designs lean on carbon-based shielding. But the ceiling is unavoidable. A spacecraft light enough to be pushed to relativistic speed by a laser is, by definition, too thin to carry heavy armor. It survives its own velocity only by slowly being sacrificed to it. Now push the speed further, toward what a crude interstellar mission would actually need to make the journey survivable within a human lifetime. And the same interstellar hydrogen that merely erodes a small probe becomes something else entirely. In 2012, physicists William Edelstein and Arthur Edelstein modeled what a starship's hull would experience from ordinary hydrogen atoms drifting in interstellar space. Once relativity concentrates and blue shifts the energy of anything a fast-moving object collides with head-on. At half the speed of light, they calculated, about 10 centimeters of aluminum hull is enough to absorb the resulting proton bombardment, and the dose rate works out to something survivable, on the order of 1,000th of a sievert per hour. Push to 90% of light speed, and that same interstellar hydrogen delivers a dose rate of roughly 1,000 sieverts per hour. An acute whole-body dose above about 6 sieverts is fatal. At 99% of light speed, the figure climbs past 10,000 sieverts per hour. A lethal dose in a fraction of a second, hull or no hull. And the aluminum hull that worked at 0.5 C isn't a fix that simply scales up with more of the same material. Thick enough shielding, hit by high enough energy particles, can itself become a hazard, as the incoming radiation collides with shielding atoms and sprays out a shower of secondary particles on the other side. Real spacecraft radiation shielding research, including work behind the water-filled protective barriers tested aboard the International Space Station, runs into exactly this limit. Passive mass helps considerably against the lower energy particles thrown off by solar activity, but it does very little against the highest energy galactic cosmic rays, and at relativistic collision energies, more mass can make the secondary particle problem worse rather than better. This is the opening loophole collapsing in real time. The closer a ship pushes toward the speed that would make relativistic time dilation actually useful, meaningfully shrinking the subjective length of the trip, the more completely ordinary, harmless interstellar hydrogen turns into a particle beam that no plausible shielding can stop. And even at the survivable 0.5 C, The time dilation payoff is modest. A traveler moving at half light speed experiences only about a 15% reduction in elapsed time relative to the people left behind. Nowhere near enough to make a multi-decade or multi-century voyage feel short. Going fast enough to shrink the trip and going fast enough to survive it turn out to be very difficult to have at the same time. And even a hypothetical spacecraft that solved radiation completely still runs into two more hazards that have nothing to do with particles at all. The first is distance acting on information itself, and the progression is visible in real missions long before anything reaches interstellar space. A signal to Mars, depending on where Earth and Mars sit in their orbits at the time, takes anywhere from about 3 to 22 minutes one way, already too slow for a rover to be joysticked in real time, which is why Mars rovers largely drive themselves. Push out to Pluto, and the gap grows again. When New Horizons flew past Pluto in July 2015, at a distance of about 39 astronomical units, a radio command took roughly 5.5 hours to arrive, and confirmation that it worked took another 5.5 hours to come back. Nearly half a day round trip, for a world still comfortably inside our own solar system. Voyager 1's own radio link is the clearest demonstration of where that trend leads. As the spacecraft has receded, the one-way delay for a command sent from Earth or a status report sent back has stretched past 23 hours as of 2026, on its way to a full 24-hour light day by that November. At interstellar distances, there is no such thing as real-time control. If something goes wrong, 170 astronomical units away, mission control finds out nearly a full day later, and any correction takes another full day to arrive, by which point the situation has already changed. Real missions are already adapting to this. NASA's Perseverance rover on Mars runs an onboard self-driving system, AutoNav, precisely because the round-trip communication delay makes joystick control from Earth impractical, even at Mars's relatively modest distance. Scale that same problem up by a factor of thousands, and a ship bound for another star, years away at an absolute best, has to make its own decisions alone, entirely without human oversight, for the full duration of the voyage, or accept that nothing done from home will ever arrive in time to matter. The second hazard is simpler, and in its way more absolute. Power runs out, and nothing can fix that from 25 billion kilometers away. Voyager 1 launched in 1977, carrying 10 operating science instruments powered by radioisotope thermoelectric generators, devices that convert the steady heat given off by decaying plutonium-238 directly into electricity through a bank of thermocouples, with no moving parts to break down. That decay isn't a malfunction, it's physics, and it is relentless. Following a fixed radioactive half-life, no engineering can slow. The generators lose about 4 watts of usable power every year, a slow, predictable drain with no way to refuel or repair it from Earth. To keep the spacecraft's heaters and transmitter alive, engineers have had to shut down instrument after instrument over the decades. As of 2026, only 2 of the original 10 remain switched on. Nothing failed, nothing broke. The spacecraft is simply, slowly, running out of watts, and the same math applies to any interstellar probe using current power technology, not just this one. Build it with today's best radioisotope generators, send it far enough, and it goes dark on a fixed schedule, set the day it launched, regardless of how well everything else on board performs. There is, underneath all of this, one genuine loophole, and it's worth walking through carefully, because it's the reason interstellar travel isn't simply impossible, just brutally constrained. Imagine 2 people, Alice, who stays on Earth, and Bob, who boards a spacecraft capable of reaching 99.5% of the speed of light. Bob's ship accelerates away, travels for what feels to him like 5 years, then returns. When Bob steps off the ship, Alice has aged not 5 years, but roughly 50. This isn't a story about clocks running slow in some abstract sense. From Bob's perspective, his 5 years passed entirely ordinarily, lived one day at a time. It's that time itself passed at a genuinely different rate for each of them. A real, measured consequence of relativity called time dilation. And at 99.5% of light speed, the ratio between their experienced time works out to almost exactly 10:1. Bob would notice other real effects too: relativistic aberration, another well-established consequence of the same physics, would visually compress the starfield ahead of his ship into a bright, crowded patch dead center of his forward view, while the sky behind him emptied out. The same underlying blue shift, in other words, that turns harmless interstellar hydrogen into the lethal bombardment described earlier, simply made visible. This isn't only a thought experiment either. In October of 1971, physicists Joseph Hafele and Richard Keating flew a set of atomic clocks around the world aboard ordinary commercial airliners, once eastward, once westward, and compared them afterward to a reference clock that stayed on the ground at the US Naval Observatory. The clocks that flew came back reading measurably different times than the one that stayed put, differences of only tens to a few hundred billionths of a second, but differences that matched the predictions of relativity. It's a small, almost absurdly modest effect at the speed of a passenger jet, nowhere close to Bob's 5-year, 50-year gap, but it proved the mechanism is real, measurable, and not just a mathematical convenience. Alice and Bob's version of the same effect simply requires a speed and duration no commercial aircraft could ever approach. The mathematics continues relentlessly in either direction. Dilation, this dramatic, requires speeds close enough to light that they run headlong into the radiation problem from a few minutes ago. The universe doesn't appear to let anyone have the time-saving benefit of relativity without also handing them the bill for it. So is there any real answer to the radiation problem, short of simply accepting a slower, safer speed? A handful of serious research groups have tried. Between 2013 and 2015, a European Union-funded initiative called SR2S, Space Radiation Superconductive Shield, worked with CERN, the same institution behind the Large Hadron Collider, to study whether a superconducting magnetic field, rather than solid mass, could deflect charged cosmic ray particles away from a crewed spacecraft, the way Earth's own magnetic field deflects the solar wind. The concept is real, and the underlying physics is sound in principle. Magnetic fields genuinely do bend the paths of charged particles, the same way Earth's own magnetic field routes the solar wind harmlessly around the entire planet. But the engineering has never left the laboratory. Producing a field strong enough to matter means large superconducting coils, which means active cooling systems, which means mass and power draw stacked on top of a spacecraft that was already fighting the rocket equation before any of this was added. No shield of this kind has ever flown, and none of the concepts studied so far come close to the field strengths that would be needed to deflect the blue-shifted, high-energy bombardment a ship moving at any meaningful fraction of light speed would actually face. It remains honestly an unsolved problem, one of the real open engineering questions standing between us and any crewed interstellar mission, relativistic time dilation or not. And it circles back to the very first equation in this film. Tsiolkovsky's rocket equation doesn't care why a ship needs to be heavier, only that it does. Every kilogram spent on magnets, coolant, or shielding is a kilogram not spent on fuel, deceleration capacity, or the crew itself, which means the radiation problem and the propulsion problem were never really separate problems at all. They're the same problem, argued over the same mass budget. Let's pause here and put real numbers on real destinations, because the hazard math shifts with every one of them, and it's worth watching every hazard from earlier in this film compound at once. Proxima Centauri, the nearest star beyond our own sun, sits 4.24 light-years away. At a hypothetical, still survivable 0.5 C, the ceiling the Edelstein and Edelstein-Hull calculation allows, that trip takes about 8.5 years of Earth time, and thanks to modest time dilation, slightly less than that for the crew, call it just over 7 subjective years. Radiation exposure at that speed stays in the survivable range described earlier. The one-way communication lag climbs from minutes to years almost immediately after departure, meaning mission control effectively loses the ability to help within the first weeks of the voyage, and a spacecraft's onboard power systems would need to run reliably, unrepaired, for the better part of a decade. Life support alone is a real, unresolved piece of that puzzle. Closed-loop water and air recycling systems, of the kind flown continuously on the International Space Station, have accumulated years of real operational data in low Earth orbit, but never anywhere close to a decade of total isolation, with zero resupply, zero replacement parts, and zero possibility of an emergency return. Difficult, but at least conceivable, if every open engineering problem described so far were actually solved. Push the destination out to the center of our own galaxy, roughly 26,000 light-years away, and the picture changes entirely. Reaching it within a human lifetime at all requires speeds deep into the lethal radiation regime from earlier, 99.5% of light speed or beyond, at which point Edelstein and Edelstein's shielding math no longer offers any real protection. Even setting that aside, the trip takes about 26,100 years back on Earth, compressed for the crew, by that roughly 10-to-1 dilation ratio, into a still enormous 2,600 subjective years, longer than the entire span of recorded human history. No human crew, however the radiation problem got solved, survives that trip, and no mission control back on Earth would exist in any recognizable form by the time a signal, sent at the moment of arrival, could even complete its 26,000-year return journey. And Andromeda, our nearest large galactic neighbor, sits about 2.5 million light-years away, itself approaching us, as it happens, on a collision course with the Milky Way that current measurements place several billion years in the future. A reminder that even galaxies aren't fixed points on a map, so much as objects in motion, on timescales that dwarf anything discussed so far. At 99.5% of light speed, the crew's own subjective experience of the Andromeda crossing still comes out to roughly 250,000 years, longer than the entire existence of Homo sapiens as a species, let alone any civilization capable of remembering why the ship was sent. Every step outward doesn't just add distance. It multiplies every hazard already on the table: more radiation exposure, more communication lag, more time for a power source to fail, and a subjective travel time that, past a certain point, simply exceeds anything a human body or a human civilization back home could reasonably wait out. And even this understates the problem, because the universe has one more mechanism at work that has nothing to do with engineering at all. In 1998, two independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and including Adam Rees, were separately studying distant Type Ia supernovae, the thermonuclear detonation of a white dwarf star that has pulled in just enough extra mass from a companion to cross a well-defined physical threshold and explode, every time at very nearly the same peak brightness, making them bright and consistent enough to serve as a reliable cosmic measuring stick, sometimes called standard candles, for distances far beyond what other methods could reach. Both teams found the same shocking result. The universe's expansion isn't slowing down under its own gravity, as almost everyone had assumed. It's speeding up. The discovery was significant enough that Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics for it. The mechanism is still formally labeled dark energy, a real, measured effect whose deeper cause remains unresolved, though observations from missions like Europe's Planck spacecraft put its share of the universe's total energy content at roughly 68%, making it, by a wide margin, the single largest component of everything that exists. Space itself is expanding at a rate cosmologists estimate at somewhere around 70 kilometers per second for every 3.26 million light-years of distance, a number small enough to be irrelevant across a solar system, and large enough to dominate everything once distances stretch into the billions of light years. That has a strange consequence for travel, and it's worth sitting with, because it changes the shape of the entire problem this film has been building toward. Every hazard described so far, the radiation, the erosion, the communication lag, the slow death of a power source, is a hazard a sufficiently advanced, sufficiently well-funded, sufficiently patient civilization might, in principle, eventually solve. Better shielding materials, smarter autonomous systems, new sources of onboard power. None of those problems are forbidden by the laws of physics. They're forbidden only by the current state of engineering. Cosmic expansion is a different kind of ceiling entirely. A galaxy whose light took, say, 10 billion years to reach us isn't 10 billion light years away anymore. While that light was in transit, the space between here and there kept expanding, so the galaxy's actual present-day distance is now considerably larger than the light travel time distance suggests. Carry this far enough, and you reach what cosmologists call the cosmic event horizon, a real, calculable distance, estimated today at roughly 16 billion light-years, beyond which no signal and no spacecraft, moving at any speed up to and including light speed itself, can ever arrive, because the space between here and there is expanding faster than anything could cross it. It isn't a matter of a better engine or a thicker shield. Past that horizon, arrival isn't merely slow, it is mathematically impossible for anyone, ever, regardless of the technology available to them. Engineering has a ceiling. This is the ceiling above the ceiling. Put that number next to everything else in this film, though, and something worth pausing on becomes clear. Andromeda, at 2.5 million light-years, is a rounding error against a 16 billion light-year horizon, about 6,000 times closer. Even the galactic center, at 26,000 light-years, is closer still. Cosmic expansion is the true, ultimate ceiling on where a traveler could ever arrive. But for every real destination discussed in this film, it was never the ceiling that actually mattered. Radiation, erosion, communication lag, and a slowly dying power supply all impose their limits at distances vastly smaller than the point at which the universe itself would first say no. All of which forces an honest, human choice, not just a physics answer. A traveler willing to accept a one-way trip, never returning, never reporting back on any time frame that matters to the people who sent them, can, within a single subjective lifetime near light speed, reach a genuinely staggering fraction of the observable universe, precisely because of the same time dilation that makes the twin paradox real. Every hazard from earlier in this film is still present on a one-way trip: the radiation, the erosion, the eventual silence of a dying power source. But there's no return leg to survive. No reunion to time, no civilization back home whose recognition still needs protecting. The math doesn't care that nobody back home will ever learn what was found, but a traveler who wants to return to a civilization that still recognizes them, parents, children, a language, a culture, a functioning Earth to land on, is boxed in far more tightly. Round-trip radiation dose, doubled. Round-trip mission length, doubled, with no possibility of resupply or repair on either leg. And every one of the hazards from earlier in this film, the erosion, the power decay, the shielding that was never quite good enough, given twice as long to accumulate. And the elapsed time back home, even accounting for dilation, likely measured in centuries at best, for anything beyond our closest stellar neighbors. A return to a world that has moved on without you, however briefly the journey felt from inside it. Even Proxima Centauri, the nearest realistic destination in this entire film, means arriving home to an Earth that has aged by nearly 2 decades, while the crew lived through less than a decade and a half of it. That isn't a limitation solved with more thrust. It's a choice a traveler, or a species, has to make deliberately. How much are you willing to give up, permanently, for how far you're willing to go? So the fastest thing humanity has ever built still needs roughly 6,500 years to reach our nearest neighboring star. Push toward the speeds that could shrink that number to something a human life could hold, and the universe hands over a bill: hydrogen atoms that erode a hull, radiation that turns lethal at exactly the velocities that matter, a signal delay that erases any real chance of rescue, a power source that runs down no matter how carefully it's rationed. Go far enough, fast enough, to outrun all of it, and there is still a horizon past which arrival simply isn't possible for anyone, at any speed, ever. None of this is a failure of imagination, and none of it is a reason to stop looking outward. It's simply what the universe is actually built like, not hostile exactly, in the way a storm or a predator is hostile, but indifferent in a way that turns out to feel almost the same from the inside of a spacecraft. Distance was never just an inconvenience waiting to be engineered away. It is, in a very real sense, the shape of the danger itself, close to home, survivable, a little farther, costly, farther still, lethal, and past a certain honest, calculable point, permanently out of reach, for anyone who has ever tried to make the crossing. Consider what that actually means. Every spacecraft humanity has ever launched, every signal ever sent, every plan ever drawn up for a ship to the stars, has taken place inside a tiny, survivable pocket near one ordinary star, in one unremarkable corner of one galaxy, among trillions of others scattered across a universe whose true, present-day scale still exceeds what most people ever picture when they look up at a clear night sky. The danger doesn't announce itself as a wall. It arrives quietly, one erosion measurement, one dose reading, one dead instrument at a time, until the honest total is impossible to ignore. And maybe that's the quiet lesson underneath all the math. Not that the universe is cruel, but that it is exactly, precisely, unforgivingly consistent. The same rules, everywhere, for everyone who has ever tried to leave, and the same rules waiting, unchanged, for whoever tries next.